Greetings to all corners of the world. Welcome to my talk about fully computable a posteriori error bounds for eigenfunctions. My name is Tomas Vejchodsky. I am from the Institute of Mathematics of the Czech Academy of Sciences. And this is a joint work with Shuefeng Liu from Niigata University, Japan. This talk is a part of the workshop Recap 2022 organized by Waseda University. So let me introduce my talk. It's about guaranteed and fully computable a posteriori error bounds for elliptic eigenvalue problems. We will be interested in this abstract formulation of the elliptic eigenvalue problem. At the moment, imagine just a Laplace eigenvalue problem with eigenvalues lambda I and eigenfunctions ui. And for these eigenvalues and eigenfunctions, we want to compute guaranteed upper bound. So for eigenvalues, it means to compute a number eta that bounds the difference between the exact eigenvalue and the approximate eigenvalue lambda I. So this task is actually equivalent to computing lower bound and upper bound of exact eigenvalues. This is a well-known and very well-studied problem to compute two-sided bounds of eigenvalues. It goes back to works of Cato in 1940s, Lehmann 1940s, 1915s, Gerisch and his Lehmann-Gerisch method, and so on. So in the recent years, there was a lot of interest in these problems, and people that contributed to this topic are present at this workshop. Let me mention Martin Wohralik, for example, or Shuefeng Liu, Carstensen together with Joscha Gedicke have very nice results, very nice method how to compute lower and upper bounds, and also others like Huschier, Michael Plum, of course, and others. Good. At this talk, I will not be interested so much about the lower and upper bounds of the eigenvalues. I will concentrate on the error in eigenfunctions. I will actually assume that I already have computed these lower and upper bounds of eigenvalues, and I want to use these bounds to find a guaranteed bound on the error in eigenfunctions. So you may imagine the difference between the exact and approximate eigenfunction, ui minus ui hat, in the energy norm, denoted with this index A. But this is not a good idea for multiple tight clusters of eigenvalues. This is good for simple eigenvalues, but if the clusters are tight or eigenvalues are multiple, then these corresponding eigenfunctions are very sensitive to small changes of the problem itself. So the problem to find such eigenfunction is actually ill-posed, and to bound an error of the solution of ill-posed problem is not a good idea. Much better idea is to consider spaces. So we consider a cluster with eigenvalues lambda lowercase n up to a lambda capital N. And then we consider a space capital E of exact eigenfunctions corresponding to these eigenvalues lambda n up to lambda capital N. And also a space E hat of approximate eigenfunctions corresponding to these eigenvalues. And our goal is to consider a consider a distance between this space of exact eigenfunctions and approximate eigenfunctions. This distance is denoted by delta, and we want to compute some really guaranteed and computable upper bound. So together with, just a setting, just to explain what this eigenvalue problem is about. This is the abstract formulation of my eigenvalue problem, and it's actually defined by two Hilbert spaces, V and W, and by the two scalar product in these Hilbert spaces, which I denote by A and by B. So A is the scalar product in the Hilbert space V, B is the inner product in the Hilbert space W, and these two Hilbert spaces are connected by a compact operator gamma. Gamma maps V to W, and it's really crucial that this operator is compact. It's our assumption, and everything is based on that. So given the spaces and the corresponding inner products, we can consider this abstract eigenvalue problem of finding eigenvalues lambda I and corresponding eigenfunctions ui, such that A ui v equals lambda I, B gamma ui, gamma v for all test functions v in the Hilbert space V. So it might look very abstract, but if we imagine the Laplace eigenvalue problem, for example, it fits very well. Actually, the weak formulation of the Laplace eigenvalue problem fits very well to this setting. We just choose the Sobolev space H10 omega for V. We choose the L2 omega space for W. A is the corresponding scalar product in H1 omega. B is the standard L2 product in L2, of course, and gamma is just the identity operator from the Hilbert space H10 to L2. So if we use this setting in our abstract formulation, we end up with this inequality, with this equality, which I believe is very familiar to every one of you. It's just the weak formulation of the Laplace eigenvalue problem that I formulated here, right? So this is just to get you a little bit used to my notation, to this abstract eigenvalue problem that we are trying to solve. Right, and together with Xuef and Liu, we derived this bound for certain distance delta A between the space of exact eigenfunctions and approximate eigenfunctions. For the later reference, I denote this bound by bound 1. And let me now explain what are these symbols and how to read this bound. So what we have on the left-hand side. You have the two spaces. E capital K corresponds to the space of exact eigenfunctions for the cluster of for our cluster of interest. And this capital A corresponds to that index of that cluster, right? E hat K is the corresponding space of approximate eigenfunctions we already talked about. Actually, the only assumption about the approximate eigenfunction is that these approximate eigenfunctions are linearly independent. And I don't need to know much more about these eigenfunctions. So good. I want to talk a little bit more about this distance delta A square. This is called a directed distance, and it is defined by this formula. You can see that this formula is not symmetric, and that distance in general is really not symmetric. But it can be shown that if the dimension of the two spaces there is the same, then that the directed distance is really symmetric, and it coincides with the quantity known as the gap between the two spaces. I also want to point out that this directed distance can be expressed in several different ways. One of the possibilities is to express this directed distance as this operator norm of this composition of projections. P hat is the projection, orthogonal projection in the energy product to the space E hat K, and capital P is the same orthogonal projection to the space ek. So if we have orthogonal projections to these two spaces, we can evaluate this number as a corresponding operator norm of these projections. This will be useful later on in my talk. Good. So this is on the left-hand side of my bound. So what we can see on the right-hand side, we have the number row there. It's nothing else, just the lower bound on the n plus first eigenvalue, and we assume that this lower bound is known, so we have it, no problem. Lambda n hat with index k is an approximation of the largest eigenvalue in my cluster. It's computed as a maximum over the corresponding Rayleigh quotient, so it's very easy to compute. Lambda n is the smallest eigenvalue in my cluster, and I assume that I know good lower bound and good upper bound on all my eigenvalues. So even to lambda n, so using this lower and upper bound, I can easily evaluate this guy here. And the final quantity that I did not explain is this theta a, this index k. This is a quantity that reflects the errors in the previous clusters, in the clusters that are below my cluster of interest. I don't want to go to the details, so just tell me that this quantity can be easily computed. It depends on the errors that I have to estimate in my previous clusters. Very good. So looking at this bound, we can see that it can be computed very quickly, very easily. However, it has some drawbacks. Here you can see that this lambda capital N is virtually, well, it is an approximation of the largest eigenvalue in my cluster, and this lambda lowercase n is the smallest eigenvalue in the cluster. So the difference is the size or the width of my cluster of interest. So it means that if I refine my mesh, I compute more and more exact approximations. The distance delta A of the two spaces will go to 0, but the right-hand side here will go to the width of the cluster. So this upper bound in general is not convergent, which is unpleasant. And also this accumulation of errors from the previous clusters make this bound less and less accurate if we increase, if we go up with the clusters. For higher and higher clusters, somehow these errors accumulate, which is again not very nice. So we were motivated by these problems to find a bound that does not suffer from this. But before I will get there, let me just mention that we have a similar bound for the distance that is not measured in the A norm, but in the B norm. So this delta B is defined in the same way as delta A, except that here and here we have the B norm. And the upper bound for the B norm is virtually the same. It has the same structure, the same problems. And the last bound I want to show at this point is this one. It is motivated by the well-known identity that relates the error in eigenfunctions in A norm with the error in the B norm and with the error in eigenvalues. This is quite well-known identity, and if you generalize this identity to these directed distances delta A and delta B, you end up with this inequality. Which is interesting because it bounds the error in the A norm by the error in the B norm. So if we use the bound on the B norm from the previous slide and use it here, we obtain a second alternative bound for the norm in the A norm. And it turns out, I will show it at the end in numerical examples, that this second bound, bound 2, is actually more accurate, it's often more accurate than the bound number 1. All right, as I mentioned, these bounds that I have shown have some say problems or weak points, and we tried to remove them. We succeeded by using the Davis-Kahan sine theta theorem together with Prager-Sinche technique, and I would like to present it now. For that reason, I need some notation. So first of all, let me introduce the solution operator capital T. It's a really crucial notion. Imagine here a big formulation of an elliptic problem. U is the right-hand side of that problem, and here TU is the solution of this elliptic problem, right? That weakly formulated elliptic problem. So therefore, well, and this solution is of course uniquely defined for all right-hand sides. So this solution operator TU is well defined as an operator from V to V. Very good. The solution operator is compact and self-adjoint. So therefore, we can use the spectral theory of compact operators to guarantee well-posedness of our abstract eigenvalue problem. So it's really a crucial notion. The point is that this solution operator may have a large kernel. There could be a lot of functions in my space V that map to 0. And I want to avoid these functions. Therefore, I define space U that is an orthogonal complement to the kernel of T. Just note that the kernel of T is the same as the kernel of gamma, this compact operator gamma. So U can be defined as well as the orthogonal complement of kernel of gamma. So why do I do that? Because if I restrict my solution operator T to the space U, I obtain an invertible operator. So I denote its inverse by A. Operator A maps U to U, and it has this property, this identity AUV equals B, gamma AU, gamma V holds for all UV in U. You can see that it is virtually the same identity as here, as in the definition of the solution operator T, except that we have T here, and in this identity we have the inverse of T on the other side. This identity, if we use this identity in the weak formulation of our eigenvalue problem, we immediately see that our abstract eigenvalue problem is equivalent to the eigenvalue problem for the operator A. AUI equals lambda I UI. So this is an alternative formulation of our abstract eigenvalue problem. Now we consider a discretization of this eigenvalue problem. So we consider a discrete operator from E hat to E hat, where E hat is the space of approximate eigenfunctions. This discrete operator has an analogous property as the exact operator A, except it's just in the space E hat. And of course, the approximate eigenvalue problem is the eigenvalue problem for A hat. Good. And two last notions. The first one is the negative norm. I define the so-called negative norm by this formula. So it's defined using the scalar product B and the energy norm induced by A. So this is a norm in the space U. Finally, let me define the alternative distance. Except of the distance delta A and delta B, we define a distance delta tilde, which is defined in the same way as delta A. This is the same formula, except here we don't have the norm induced by A, but we have the norm induced by the inner product B, right? So this alternative distance is very similar to the A distance, delta A distance, and there is really a clear correspondence between delta tilde and delta A. Good, so using this notation, we can finally formulate our next bound. It is here, that the delta B distance of spaces E and E hat can be bounded by this epsilon times this delta tilde that I have just defined. There are some assumptions. First of all, I need this sigma. Sigma is a spectral gap. It is a number that corresponds to the gap between the eigenvalue lambda n minus 1, which is one below my cluster of interest, and lambda n hat, which is an approximation of the first eigenvalue in my cluster. And in a similar way on the other side of the cluster. This is the next eigenvalue after my cluster, and lambda n hat is the approximation of the eigenvalue that is the last one in the cluster. So the difference corresponds to the gap between the cluster and the next eigenvalue. So that's the sigma. And epsilon is a quantity that measures the residual. It measures the residual in that negative or dual norm that we have just defined. So yeah, here is the projection to the space E. Here is the projection to the space E hat. And here we have the difference between the exact operator A and the approximate operator A. So it really corresponds to the residual. So this epsilon is sort of a measure of the residual. So why is this bound on delta B is so interesting? Well, because this delta tilde can be bound like this using delta B. So if we now combine this estimate of delta tilde with this bound, we obtain a quadratic inequality for delta B. This quadratic inequality can be solved. Here you can see the solution. So delta B can be bounded by this formula where alpha 1 and alpha 2 depend on epsilon. So once we know what epsilon is, we can compute delta B. And that epsilon that is defined here, that negative norm of the residual, can be bounded by the well-known Prager-Singer technique or hypercycle technique or flux reconstruction technique, or this technique can have different names, but I believe that it's quite well known for you. The point is that this technique depends on the problem. So here this formula works for the Laplace eigenvalue problem. If you don't have just Laplace eigenvalue problem, but some different operator, you can apply the technique, but the formulas looks a little bit differently. So just to show you the result, we need the H-diff space, and here we have formulated in terms of a finite dimensional subspace of H-diff. And the conclusion is that the quantity epsilon is bounded by 1 over sigma max min of this identity, where this pH is known as the flux reconstruction. Here it is formulated that we are looking for the best flux reconstruction in the finite dimensional space VH that minimizes this upper bound. Well, it's not necessarily to compute the absolutely best approximation because it might be costly. We can use some flux reconstruction that is done locally and results to a value that is close to the minimum, but much faster. Here, this maximum is actually corresponds to a small eigenvalue problem. The size of that eigenvalue problem equals to the dimension of this space E hat, so equals to the number of eigenvalues we have in our cluster of interest. So once we have this flux reconstruction pH, we can fairly easily evaluate this upper bound on epsilon, and that epsilon, if I go back, will help us to bound delta B. Good. So one point about this bound is that it depends on this inequality for delta tilde. And here you can see lambda capital N minus lambda lowercase n. So this bound still depends, not in a strong way, but it still depends on the width of our cluster. So let me just quickly show you that even this dependence can be removed. And we succeeded by applying the Davis-Kahan theorem to the solution operator T. So just very quickly, if we have that solution operator T that we already defined, and the approximate solution operator T hat, which is actually the inverse of A hat, the discrete operator A hat, then our eigenvalue problem corresponds to this eigenvalue problem for the solution operator, except that here we have the reciprocal values of our eigenvalues, and the same for the discrete solution operator T hat. The difference is that the quantity sigma, that spectral gap, now corresponds to the reciprocal values of eigenvalues, not lambdas themselves, but to 1 over lambda. Now this is a technicality, and using that sigma, we can straightforwardly bound the error measured in the energy sense by the A norm of the residual, but this is the residual for the solution operator, that is the inverse to the operator A. Okay, so what to do with this residual? Well, this residual can be bounded again by the Prager-Singer technique, which, as I said, depends on the concrete operator. So for Laplacian, the bound looks like this. It is very similar to the bound we saw 2 slides ago, except that instead of the operator A hat that was here, we have the operator T hat, which is there, which is just a technicality. We can compute this upper bound virtually in the same way as the one before. All right, so we are approaching the end of the talk. The final part is a numerical example. This is the Laplace eigenvalue problem on a square, on a unit square, 0, 1, with 0 Dirichlet boundary conditions. The exact eigenvalues of Laplacian on a square are very well known. You can see them here, and we cluster the eigenvalues into 4 clusters of interest. This is the first one, containing just 1 eigenvalue. The second cluster contains 2 eigenvalues. It's a double eigenvalue. The third cluster is again a simple one, and cluster 4 is double. We use the standard linear conforming finite elements to solve this eigenvalue problem numerically. So UH1, UH2, and so on are these finite element approximations. And based on them, we compute our bounds. And here are the results. This table shows indices of effectivity. Indices of effectivity are just simple fractions where I divide the bound, the computed bound, by the exact error, that is in my case delta A, the error measured in the energy sense. And for the meshes of these sizes, I found that for the first cluster, for the first eigenvalue, the bound number 1 and bound number 2, these are the simple ones. They provide index of effectivity 1.29, while the third bound that was based on the Davis-Kahan theorem and Prager-Sinche approach, that bound is very accurate. The index of effectivity is almost 1. For the second eigenvalue, for the second cluster, which consists of 2 eigenvalues, I'm sorry. For the second cluster, the indices of effectivity are a little bit larger than for the first one. For the first bound, the second bound improves it, but the last one is again almost exact. And we see a similar behavior for the third and the fourth cluster. The bound number one is losing accuracy. It overestimates the error more and more. The second bound improves that, which is fine, but the third bound, based on the flux reconstructions and the Davis-Kahan theorem, it provides almost exact bounds. All right, so to conclude, we considered a general abstract eigenvalue problem, and we derived fully computable upper bounds on the directed distances of spaces of the exact and approximate eigenfunctions. We had 2 kinds of bounds. The first family of bounds was very simple in the sense that it was very quick to evaluate, easy to evaluate. However, the accuracy of these bounds is limited, but still, in my opinion, useful in some applications. And we also presented a bound that is based on the Davis-Kahan theorem and Prager-Sinche approach. That bound is more complex in the sense that it takes more effort to compute it, but it provides very, very high accuracy. So finally, let me mention that what I have spoken about is published in the preprint that we have on arXiv together with Xue Feng Liu. Let me mention that our simple bounds are motivated by the results of Birkhoff and others from 1966. So it's really old stuff. And as I mentioned, the bounds, the better ones, the more accurate ones, are based on the Davis-Kahan work from 1970s. I want to also point out that a similar approach was published by these authors. Among them, Martin Vohralík is present at our workshop, and I believe he will present his approach in his talk. So this is all from my side. Thank you everyone for watching.